Hello, and welcome to this video series about the Capacita Programming Language. This is a language that I designed and implemented myself, and I've been working on it for the past few years in my free time. We're going to start by going over Capacita syntax and what this language can do. Eventually, we will examine the source code of a medium-sized program written in Capacita. Finally, I will explain how the language works, and we will take a look at the internal implementation. All right, so 2 plus 2 is 4. We can use parentheses to group operations. So as you can see, without the parentheses, we get different answer because the multiplication happens first before the additions. We can use floating point numbers with decimal expansions. So 4:3 means 4:3 ratio. It's the same as the fraction 4/3. So we can do ratio arithmetic. If you take a ratio and you divide it by an integer, you still get a ratio. But if you use the division operator, like this, you just get the decimal expansion. A float plus a ratio is a float. We can assign to variables like x, 2 times x is 10. We can assign a string to x. So x is a dynamic variable. Do a little string concatenation. We can set it back to an integer. So now it's 10. We can specify the type of a variable if you want. So if you do declare the type of a variable, it's not a dynamic variable. It can only hold one type. So if we take z and assign the string Joe, you can't do that because z is always an integer. And greeting is always a string, so you can't just assign a number into it. But we can still reassign any integer to z. And we can also assign any string to greeting. That's okay, because the types match up. So you can mix and match dynamic typing and static typing, essentially. Let's define our first function. Subroutine plus 1 returns n plus 1. That takes 3 lines, so if you want to do it in 1 line, you can have a 1-line function like this. We can reassign functions. Functions are first class. You can just store them into ordinary variables and still call them. So x is still 10. Let's do some control flow. When x is 10, print something. If x is 2, print something. In this case, x is not 2, so it doesn't do anything. So the when statement only executes the next line if the condition is true. We have the traditional if statement. So an if statement must be closed with an end. The else is optional. So when is really just the shorthand for an if statement. When does not need to be closed with an end statement. All right, let's define a factorial. Factorial of 4 is 24. Factorial of 80 is a big number. You're not restricted to 32 bits. Your integers can be arbitrarily long. All right, what to do next? Let's do a for loop. This time I'm going to make sure I is an integer. I don't want it to be anything else. I times I, and then put an end statement. We can print out the squares of the first few integers. We can use a while loop, which works as you might expect. This time let's take j and increment it by 2 every time. This prints the negative odd numbers. up to negative 11. So we can declare a list, which is a data structure. It has a length of 5 because it has 5 elements. We can reverse the list. That also mutates the original list. X is still 10, so if we call methods on it, we can get 11 and 9. And you can call methods on anything, even integer literals. So everything is treated like an object. Even though the integers don't have an object wrapper around them, you could still call methods on them. It will just pick the correct function to use and it will give you back the result. We have for each loop, so you can loop over lists, you can loop over strings. All right, let's do something a little more interesting. So the Collatz conjecture says if you take a positive natural number greater than 1 and you apply this rule to it, the rule is if the number is even, divided by 2. If the number is odd, multiply by 3 and add 1. And you keep doing this for every term in this sequence. And the conjecture, the actual conjecture is, well, this will always terminate in 1. 1 will be the last term in your sequence. So what if it doesn't terminate? What if it goes on forever? Well, nobody has proved that mathematically. So it looks like we haven't found any numbers where this doesn't terminate, but we can't be sure until somebody creates a proof that, these sequences always terminate for any natural number greater than 1. So let's finish defining this function. We can give it an argument, and we can see a sequence of numbers. It ends in null, and the reason for this is because every void function, any function that doesn't return anything, it just returns null. So null is the placeholder empty value. So all void functions return null. And that's why you're seeing the null at the very end. We can print prime numbers up to a certain maximum. This time I want to make sure the parameter has type int, so we can only pass in integers. We can do another for loop. Plus plus will increase a variable by 1. So 2 is the first prime number, but any other even number can't be prime. So if it's not 2 and if it's not 2 and it happens to be even, we just continue the for loop because we don't want to do any extra work if it's an even number, because even numbers are never prime unless it's the number 2. 2 is the only even prime. But now if it's not even, we have to make sure it's actually prime. So we take the variable k, set it to 2, and while k is less than the square root of n, notice n to the power of 0.5, that's equivalent to square root of n. So we check all the numbers up to the square root of n. If it divides evenly, if n divided by k has a remainder of 0, we know it's not prime because we just divided it and we found that we had a remainder of 0. So if it's not prime, we have to break the loop, the innermost loop, not the outer loop. And we have our variable is prime. If it's actually prime, we want to print the prime number, because the point of this function is to print all the prime numbers up to a certain maximum. So we show that. Show is just the same as print, except show does not put a new line after whatever was printed. So we can print the primes up to 100. All right, cool. So now let's just read off the first few numbers and put them into a list. and I want to define some numbers that I want to factor. And by factor, I mean I want to factor them into their prime factorization. So every positive integer has a prime factorization. 1 is the product of no primes, and 2 is just 2. 6 will be 2 times 3. 8 is 2 cubed, so it's 2 times 2 times 2. And so I'm writing this loop here that will tell us the prime factorization for all the numbers in our list of numbers up there. Notice we defined a list called primes and we defined a list called numbers. So we want to factor everything in numbers. So we do a for each loop on all of the numbers, and we have a while loop inside of that grabs the current prime. So you can index a list by using the array index operator. So primes of I is the ith element of primes. List indexing starts at 0, like in most programming languages. So we want to show the prime if we found one. So as soon as we find a prime number that works, we show it. Then we show a space after it. And then we want to divide out that prime number. So we take n and divide it by the prime. That will reduce n by some amount, and then we try to check for the next prime number. And we check for the next prime because this is all wrapped in a while loop. As long as n is greater than 1. If n becomes 1, we're done because we successfully factored the number. So let's increment I. If I is greater than the length of primes, we have a problem. The reason for this is we only have primes up to 17. So if we go past the end of the list, we can't really do anything else. So let's print an error message. Break 2. So what does break 2 do? So in many languages, break just breaks the loop. But in Capacita, break 2 will break out of 2 nested loops. So notice here we have a for loop and a while loop inside of that for loop. Break 2 will just break out of 2 loops. So break out the first loop and then break out of the outer loop. So it's a quick way to just finish exiting the outer for loop. All right, and we see the prime factorizations for those numbers, and we would get to 46. 46 is 2 times 23. 23 wasn't in the list of primes, so that's why something went wrong. So that's how you used numbered breaks. Cool. Well, I hope you enjoyed this this exercise, and I really hope to see you in the next video if you're interested in stuff like this. Thank you so much.